about earthquakes today, and maybe we'll even finish up. So last time we talked about seismograms and seismographs. And this is a seismogram, which is a piece of paper that is created by the seismograph that we made, at least in theory, in class. And we talked about the fact that you can see on this that it's a piece of paper that's pulled along at a continuous rate of movement, and the pen is staying stationary as the seismograph station is moving. And we can see that there is the arrival of those three different waves. P waves are the fastest, recall. They travel at about 3.7 miles per second. S waves are the next fastest. They travel at about 1.9 miles per second. So remember, they all happen at the same time. One big boom with all the three waves emanating from the point of rupture or focus at the same time. But since the speeds are different, they will, as you get away from the earthquake, there will be a progressive decrease in the, increase in the arrival time of the different waves. So in this case, we see that the P waves arrived at, I don't know, about 70 seconds, and then the S waves arrived at about 750 seconds. Now, since we know exactly the speed at which these waves travel, we can tell exactly how far away the earthquake was by just figuring out the distance, the distance in time, the difference in time between the P and S wave arrivals. So if we plot this on a map, and we'll do this with thunder and lightning again. If we do this on a map, it's possible to tell exactly how far away the earthquake is. So if we decided to make one of those seismograph machines that we talked about last class, and we are stationed at the green cross at this place in New Hampshire, then we have our earthquake, we have the seismogram that we generated, and we can take a compass and draw a circle around the point of rupture, where we are rather, and pinpoint exactly how far away the earthquake is. So where's the earthquake based on this? A lot of frowning faces, confused faces. Absolutely, you have no idea. The point is, it is on this line. It's not within the line. We're really good at telling the distance, but you don't know. It's somewhere on this line. It could be in northern Vermont. It could be right on the border of Massachusetts and Connecticut. It's somewhere exactly on that line. So it's not very helpful. What would you do if you wanted to try to figure out exactly where it was? What could we do? So we could call someone else who was building a seismograph machine for class, call them up, not the best location, right, in the Boston Harbor, essentially, and ask them, did you feel the earthquake? Yes, we have a seismogram rather from it. How far away was it from you? And so they can tell us the distance. We put a little compass point where their location was and draw a circle around their seismograph station. So again, we know that it is exactly that distance away from where they experienced the earthquake. What have we done then? Don't read this like a Venn diagram. Remember, we know exactly how far away. What have we done? Excellent. We've narrowed it down to 2 points. From an infinite number of points on one circle, we narrowed it down to 2 points. So you might surmise what we do next. What do we do next? Yeah. Yeah, third one called triangulation. Excellent. It is very common in all manner of geologic sciences to triangulate. 3 points can pinpoint a lot of different things. Call a third one. They're up in Maine, and we've now pinpointed the earthquake to pretty much the New Hampshire tolls, right? So this is called triangulation. This is how we pinpoint where an earthquake is. Again, in reality, we have this global teleseism network. We have seismograph stations everywhere, all over the world, and they all talk to each other. They're in constant communication. You may or may not know about BC's illustrious Weston Observatory, which is out at Weston. It's a premier research facility for seismograph research. Two members of our department, John Ebel and Alan Kafka, are really engaged in cutting-edge seismograph research. And your TA is actually writing his thesis on this. So you have this triangulation. You can tell exactly how far away an earthquake is. And in reality, you have lots and lots of different seismic stations that can absolutely pinpoint where the earthquake is. So we have this global teleseism network. So let's look a little bit more about the waves, really kind of from a qualitative and from a land use point of view. We'll look at what happens in these waves. What happens when these waves are going through the subsurface? And also, next, we're going to look at, or now, we're going to look at how can we predict earthquakes. This is a tremendous holy grail in the field of geology. There remains no good, reliable method in which we can predict earthquakes within this kind of golden window of an hour or two. What we have now is either too long in terms of the prediction time, or too undependable. So it's, I'm writing it's an art. It really is kind of an art. For example, anyone in an earthquake-prone area? What do you look at if you're wondering if there's going to be an earthquake? So think about other natural disasters, right? We just left the realm of volcanoes. We know based on increase in earthquakes, based on increase in sulfur dioxide escape levels, based on explosions, based on the shallowness of the earthquakes, we can predict this. We will look at hurricanes and tornadoes. We can predict within a certain possibility that they're happening. Earthquakes, we just really can't. So let's look at one thing. The position of the United States Geological Survey is that animals are not a method by which we can predict earthquakes. I want to be very clear that our government position, just position, is that animals are not a predictor of earthquakes. However, the Chinese have, with mixed success, predicted earthquakes based on erratic animal behavior. So some things such as dogs behaving really erratically, angrily barking, jumping around, being agitated. They have animals in labs in China that they're just watching their behavior to see if they can tell whether these dogs are predicting an earthquake. China did predict an earthquake within a 2-hour window and saved a lot of people. The details are in the book, but saved a lot of people by calling it, saying there's going to be an earthquake, everybody get out of the building, saved thousands of people. The problem is they made a lot of noise about it in the scientific field. We predicted this earthquake, we saved a lot of people. So then about a year later, there was another earthquake that was equally bad, and they failed to predict that this earthquake was going on. And so they were embarrassed. It was an embarrassment to the government. And so when offers for international aid came in, they said, no, it wasn't as bad as you think. It was fine, which was quite unfortunate because a lot of people died from exposure and from being trapped in buildings because the Chinese government was downplaying the fact that they failed to predict an earthquake because they were embarrassed from this. There was a guy out in Santa Cruz, a member of the United States Geologic Survey. He was also a faculty member at the UC schools. And he, in the 80s, did this really neat project where he retroactively predicted earthquakes. It was before the internet was as big as it is. And what he did was to look at lost pet ads in the newspaper. So he would take the classifieds and he would look for lost dog and cat ads. And he would then back into, there was something like 250% increase in the number of lost pets right before an earthquake. And so he published papers on this, expecting this to be a new field of research, but really kind of was unceremoniously dismissed by the scientific community. But it is the case that sometimes dogs and cats will behave erratically right before an earthquake. I have a friend who lives in San Francisco. She came out visiting. She said, Jen, if we were in San Francisco, I'd swear there's going to be an earthquake because Cobain, that's her cat, is acting really strange. I thought it was interesting. Turns out the cat had been bitten by her mother's dog, and they didn't know, so it was a different situation. But it was interesting to me as someone who, she's not a scientist, for her to look at her cat in the absence of, again, any other predictive mechanism. Snakes all come out to the side of the road and sort of ball up in these multi-species balls. Birds that are habituated to being near water will go nowhere near water. Horses have been documented to gallop around prior to an earthquake, sometimes under some conditions. We'll return to this when we talk about tsunami and what are the predictive things associated with tsunami. And the really interesting thing is with the Sumatra tsunami, the official death toll was 230,000 people. And probably, well, for reasons that we'll discuss, it was much, much higher, probably approaching 1 million people. The one thing that they failed to find in this horrible, horrible number of bodies was any animals. They didn't find any animal carcasses. So elephants that had been chained an elephant that had been chained in a zoo broke his chains, been chained for decades, broke his chains and ran away. There were deer-like organisms that were running up to high ground. So animals can also, as it turns out, see some sort of, they're thinking it's a pressure change as the wave approaches shore. So animals are used also for tsunami, which is mostly our earthquake generated. So animal behavior, one way by which some people think sometimes you can predict earthquakes, but it's not foolproof. A next thing you can do is look at the stick-slip behavior. And it turns out there's a certain certain periodicity between when an earthquake happened on a fault zone. Here is Japan, which we've talked about. We'll talk about again when we talk about tsunami, obviously. You see there are 4 plates coming together. This is why the first day of class, as I said, Japan is really a tectonic nightmare. There are 4 plates, 2 subduction zones, everything's coming together. There's the volcanoes and earthquakes. And there is this periodicity, so every so often there will be an earthquake. And you can plot it and say, okay, on this plate there is an earthquake every 30 years of some size. But can you see why that's not very helpful? Can we evacuate downtown Tokyo because there was an earthquake 25 years ago to the day? No, right? That's the absolute shutdown of commerce and of people's living. So there is a stick-slip behavior. We can tell about how often we can expect an earthquake, but that's not going to save lives because we're not going to evacuate areas because of this. So that's historical records, right? Documented earthquakes back through time. Another way that we can essentially kind of continue along with this record of earthquakes through history is to look at wetlands. Where there are wetlands around, you can potentially take this record back thousands of years, depending on how big and how deep the wetland is. So this is called trenching, and wetlands are categorized as an area of constant plant accumulation. The plants are always growing up, 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 and so you have this constant record of what was going on through time. And it turns out that when you have an earthquake, there are these jumbled up disturbance layers, they're called. So the active growing plants at the surface get all jumbled up, and you can see that. So there's an earthquake, and then the plants are growing, and then there's another earthquake. So again, all this does is to continue on with the historical record of seeing when, back through history, when there was an earthquake and about how big it was. You can dig a hole, essentially a trench, jump down into the wetland and see where the earthquakes are. Then you can carbon date each disturbance layer, and that allows, again, for more data. And the more data, from a predictive sense, if you take in statistics, the better, right? You're increasing N. The more data you have, the more accurate your prediction is going to be. However, this is, again, not a great method of prediction because of something called seismic gaps. And I'll show you some seismic gaps. So don't look at the legend yet. Just look at this map. Here we have the Ring of Fire, right? Say you decide, you know nothing about geology, you didn't take this class. You decide you're going to move out to California when you graduate. You want to go out to California where the weather's nice, everything's great, but you're scared of earthquakes. And so you see this map, and you see that the pink areas are areas where there have been a lot of earthquakes. The red areas where there hasn't been a lot of earthquakes. So if you know nothing about plate tectonics and earthquakes, where would you move if you're petrified of earthquakes? I want the wrong answer here. Where'd you move? Where there's no earthquakes, right? If you're scared of them, you don't want to be in a place where there's earthquakes all the time. But you can see now, yeah. Excellent. Yeah, that's the right answer, right? So someone who doesn't know what you all know now might mistakenly say, oh, look at Parkfield, California. There's not been any earthquakes there. That's a nice, safe place. But right, the plates are moving. And so what these red versus pink areas show is that in the pink, now you can look at the legend, is where stress is released. The plates are moving, and in the pink areas, the earthquakes have happened, so there's not a buildup of this strain. In the red areas, those are portions of the plate where, even though to the north and south, or to above and beneath, there have been a lot of earthquakes, something is causing that to stick, whether it's a bend in the fault or whatever it is. There's a bend or some locking. And so you can imagine that when that earthquake happens, it will be a lot bigger magnitude than the little ones, the relatively little ones that are happening to the north and the south. And we can plot this. Here is some data. Then I'm going to show you this back through time, 20 years ago or so you can see what's going on in California today. This is a picture of earthquakes in Parkfield, California. And on the x-axis, you just have the number of earthquakes, the earthquake rather, and then the year. And this gives you a nice sense of the fact that usually there is a regularly spaced interval. So how many years between the first and the second? About like 1860 to 1880. 20 years, right? 1881 to 1901, 20 years. 1901 to 22, 20 years. Next one came early. The next one came late, so it sort of got right back on track. So you see that this is about every 20 years there's an earthquake. Based on this, we predicted that there would be an earthquake in this range of 87 to 93. And there wasn't, and there wasn't, and there wasn't, and there wasn't. And it was interesting because people started to develop in Parkfield their kind of cultural identity based on this. If you drive into Parkfield, California, the sign says, "Welcome to Parkfield, home of the next big one." And you go to a restaurant, they have seismic burgers and sonic shakes. They're waiting for the next big one. So far from being scared of it, they hung their personal identities on this. Back in 2004, which is much later, right? Much past the earthquake that happened, or the predictive method of seismic gaps, there was an earthquake, and it was a 6.0. This is now one of the most heavily instrumented areas of a fault zone in the world, because this is an earthquake that was nowhere near as big as it should have been. And so there is, again, this notion that this will be the next big earthquake in California, because 6.0 is nothing relative to how much energy they predicted, seismologists predicted, when looking at earthquakes in the past. So a little side note, did you hear about the earthquakes in Oklahoma? Anyone hear about them? It was big. Eric, how big was it? Do you remember? 5.3? Are you here, Eric? What? Yeah, 5.4, right. So big earthquake. And this is an area that historically haven't had many earthquakes. Does anyone know why or how? Seismologists are really cagey about saying why and predicting future stuff for good reason. Some Italian scientists were jailed by the government for failing to predict an earthquake. So seismologists are really sort of skittish about saying things about this. But I'm not a seismologist, so I will. So there were some earthquakes. There are a lot of earthquakes relative to how many there have been in the past. And anyone know what it's maybe corroborated? No, you guys didn't hear about this earthquake, right? It's pretty. Nobody died, but it was pretty scary for the people that were in it. So fracking, do you know what fracking is? Yeah. We talked about fracking in Geoscience 1. If you're taking Geoscience 1 next semester, you'll hear about it. So it's putting water underneath the surface of Earth to break up rocks in situ and to get oil and gas out of the surface. It's an economically efficient way of extracting these resources relative to the historic way that we would do it by busting up the rocks, bringing them to the surface, and essentially physically separating out the oil and gas from the rock. The problem is when you do this, it's possible to lubricate fault zones or to otherwise modify the subsurface so that there could be earthquakes. And it is coming to really kind of clarity that, at least in a non-science way, that when we're fracking the subsurface, there is a large increase in earthquakes, especially in places that haven't historically had these big earthquakes. So Oklahoma is not an area where there have been historically, again, a lot of earthquakes, but we are causing them. We've caused them in other ways. We've caused them when filling dams. So again, last semester talking about the Quabbin Reservoir. Wouldn't happen with something that small, but China, when they made the Bangkao Dam, it's a big dam that they built to create a big stable reservoir for drinking water, and the filling in of that reservoir caused a huge amount of pressure to be placed in a small area on the landscape, and it broke the rocks essentially beneath it. There was a big earthquake, it caused the dam to fail, there were a lot of people that perished. So we can make earthquakes ourselves. Another thing that can happen, and this is mostly because rocks or sediments expand and pore spaces fill with water or change the rock's properties in some way. The next one as well. So we put these strain gauges in, and there's some evidence that sometimes, this is part of the San Andreas fault here, some evidence that sometimes right before an earthquake actually goes, there's a slight expansion that can be picked up by strain gauges. So this is an area of research, an active research. Now, is there something that happens right before an earthquake that we can, again, if we figure out based on strain gauges this change, we can get people out of the built environment. So again, rocks and sediments may expand. Also, water may rush up from the very deep parts of Earth. So these are things that GW stands for groundwater. These are things that have been documented to occur, again, sometimes in some situations in people's groundwater wells or in the water in the subsurface. So the levels will rise or decline rapidly right before, or the ability to conduct electric currents. What we're talking about here is conductivity, and conductivity is a measure of how many dissolved solutes are in the water. So somehow a bunch of water, maybe that's deep, comes up to the surface and it has a lot more dissolved solutes than the native groundwater at the shallow subsurface. The temperature can rise or fall. Again, along with the ability to conduct electric currents, there's a rapid change in the chemistry, and jumping down to the bottom, including radon, a radioactive gas that can suddenly appear in groundwater wells right before an earthquake. And then also slight changes in magnetic field or gravity right before an earthquake. So again, these are some things that may be related to rocks getting ready to go. So this expansion of sediments, expansion of rocks, water coming up from the pore spaces, and changing things right before. So those are some of the ways that we can try to approach predicting earthquakes, but again, not terribly effective historically. We'll return to this notion of prediction in a minute, but let's look at what kills you. So what sorts of things, again, we've established earthquakes don't kill people, buildings do. So what factors control the death toll or the damage in the built environment? This is a summary slide, so I have a slide on each one, so if you're writing this down, maybe save some space. So look at how far away you are from the earthquake, which is probably largely self-explanatory, right? But we have to combine that with things like the local geology, construction message, and then what time of day in which the earthquake went off. So we'll look at each one of these. So for example, how far away are you? This is obvious, right? If that is the focus or the epicenter of the earthquake, you're close to it, that's not a good situation. The farther away you are from the earthquake, the better, right? At some point, the waves extinguish, at least from a feeling point of view. However, you have to layer on top of this the local geology. The farther away you are, the better. The local geology is incredibly important when we're looking at how you can predict earthquakes. So, for example, we talked about the Great Fire of 1906, right? We had the 1906 earthquake in California, and there was all this damage, and fires raged for weeks. And so what they did was to bulldoze, and you read about this in your book, bulldoze the material out into the Marina district, unconsolidated sediment. So building rubble, sand, gravel. They were pumping mud and sediment from the bay to make more land. And so then they built in the Marina district. So this is showing you the San Francisco Bay, and then this is intended to be structurally sound crystalline bedrock. And this stuff here is unconsolidated sediment. So in this case, the good house was actually closer to the breaking of the rock, the fault, but because that bad house, my fake animation, is built on unconsolidated sediment, there was a horrible amount of damage in the Marina district. So the local geology is tough. The Marina district was put there again to create new land, and old buildings and all unconsolidated stuff, landfill essentially. This is exactly what Boston is built on for different reasons. And in 1989, the Loma Prieta earthquake collapsed the freeway. There were 41 people that were killed as a result of it being built on this unconsolidated sediment. So the epicenter was farther away from there, but that's where the greatest damage was done. Construction message of what is your home constructed? So it turns out, we started talking about this, you want a building to sway in an earthquake. You don't want the building to remain fixed, because then eventually the building will collapse. Brick is a terrible thing to have your house or building built of, because it doesn't sway. So buildings that are earthquake proof, they say, are made with concrete, but that have steel reinforcements. And so the building can sway in an earthquake. So how is your house built? Some areas in remote China that have had really increased death toll relative to how many there could be were built because they had mud thatched walls of their huts, of their houses, with big, heavy, ornamental baked clay roofs. So you have this big, huge, heavy roof being supported by thin, relatively flimsy walls, and pancaking, right? Kills everybody inside. So you don't want to have brick, you don't want to have mud and straw with a big, heavy, ornamental roof. You do want to have some method by which these buildings can sway. And also, just kind of dancing around the topic of resonance, matching the vibrational frequency of the earthquake to the number of stories in the building. A 2-story building in an earthquake has a high frequency, and so there will be the most damage. Turns out a very, very tall building, again, depending on what the resonance or the vibrational frequency of the earthquake is good. So looking at downtown Tokyo, you have the earthquake coming through, and every time a wave comes, it will actually stabilize the swaying of the earthquake if you have the right size. 10-story, I think it was 10-story, Mexico City, there was an earthquake, and only the 10-story buildings collapsed because that was out of phase. So every time a wave came, it actually made the moving, the swaying of the buildings worse, amplified them. So you want the waves to be out of phase and cancel out the swaying, and it will remain less sort of moving rather than in phase. So building heights are important to look at. This is something that I won't get into. It was 20-story buildings, sorry. I won't go and load this up on the internet, but if you're interested in earthquakes, this might be a good way to study and sort of drive home the concepts that we're talking about today. The Discovery Channel, so this is in the slides on Canvas, has this Make a Quake. And it's really neat. You can build this building, and then you have different foundational engineered pieces, whether it's on pilings, whether it's just in a basement. And then you can put different types of geology. So is it unconsolidated sediment? Is it nice structurally sound crystalline rock? Is it mud? Whatever it is that the building on which the building is built. And then you can create a quake of different magnitudes. So it encompasses 4 or 5 of the things that we talked about in class. And so it's fun. It's sort of video game fun to see, can you get this building to topple over? But also, if you're looking at it, you might read the description of everything that's going on, because it does sort of drive home a lot of the concepts that we talked about. So again, I won't play with it here, but if you're interested, it's a neat thing to look at. So the last part of this is not something that controls the damage, but it does control the death, population density, and the time of day. How many people are there? Where are they concentrated? So you can imagine, those of you who've been to Tokyo, how many people live in downtown Tokyo? Have residents right downtown? Virtually no one, right? They commute in on these high-speed trains, so people live in the outskirts of the city, and you come into Tokyo to work. And so you can imagine that if there was a massive earthquake in Tokyo and the buildings were heavily damaged or collapsing at 2 in the afternoon on a weekday, the death toll would be massive, relative to it being 2 o'clock in the morning. The damage would be the same, but nobody would be trapped in the buildings. Maybe some night workers, security, cleaning staff. The death toll would be smaller. So it matters what time of day the earthquake happens and where people are. An interesting example of this is in San Francisco, again, the 1989 Loma Prieta earthquake. There was a big earthquake, but relatively few people were injured. Anyone know why? This is back before your time, certainly. The World Series was being held in San Francisco, and so San Francisco traffic planners and officials were telling everyone, don't come to work today. It's going to be a zoo. There's going to be a ton of traffic. We're closing all the roads. Work from home. Stay home. Don't come in today. Again, it's going to be a big problem. So the World Series was held, and it's in an open-air stadium, and the earthquake was on. I remember seeing footage of this. It was crazy. People were so scared, crying, weeping, but it's open air, and the building, I mean, the stadium is shaking like crazy for a long time, but there's nothing above them to collapse on them. So the death toll was actually tiny. It was 63 people, and there were about 3,800 people that were injured. But that death toll, had it not been the World Series, would have been massive based on the damage to the buildings, especially in the Marina district. People just weren't there. So the population density and how many times a day, what time of day it is interesting to kind of ponder. Bottom line with regards to prediction, we are trying to learn, but earthquakes remain a very, very deadly, the most deadly in many regards, natural disaster because they are so unpredictable. So we talked about fracking. We talked about how fracking can, many people think, cause an increase in earthquakes. An interesting thing that happened in the 60s, from 1962 to 1965, there was a chemical warfare plant in the Rocky Mountain Arsenal in Colorado, and there was a whole bunch of liquid waste that they needed to get rid of as they're manufacturing these chemicals for warfare. And they got a permit to inject the liquid waste into the subsurface. So they had this this injection well, and they were injecting the waste into the subsurface as a trial way of getting rid of this waste, so it's not polluting our waterways, again, back in the 60s. And so they did this, and they had to stop this injection because there were earthquakes. So they stopped, waited for the earthquakes to go away, and then started up again with injecting. Earthquakes happened again. And it was quickly discovered that they were actually correlating the injection of liquid waste into the subsurface with slippage along the fault boundary. So they were causing earthquakes. This, again, can happen, and it happened recently this weekend in Oklahoma, Texas. Underground nuclear explosions in Nevada. We were testing nuclear weapons, triggered a 6.3 earthquake. The dams, so we talked about the China Dam, also did the Hoover Dam. There were 2 magnitude 4s associated with filling the reservoir with the Hoover Dam, and one 5.0. So we can cause earthquakes. We are continuing to cause earthquakes as a result of the things that we do. Back then in Colorado, I say it's an interesting proposal because instead of saying, oh gosh, we shouldn't do this because we're causing earthquakes, someone said, why don't we solve 2 problems at once? Why don't we solve the problem of liquid waste that we don't want and the problem of earthquakes building up to massive proportions by all over the world or all over the United States injecting our wastewater, so from a wastewater treatment plant, any sort of liquid waste we have, into the fault. So instead of this bang, huge earthquakes, we just have the faults slide past each other in a quiet fashion. Yes, we're going to have to fix a road here, a bridge there, but we won't have massive 8.5 earthquakes. And just started to gain some popularity as an idea. Yeah, we'll solve these 2 problems until, I think it was an economist, kind of rained on their parade and said, okay, well, who is going to be financially, ethically, morally responsible for killing lots of people as we transition from this situation where there are some stuck points to triggering them so they can slide past each other? And no one was willing to assume the risk of, or the financial responsibility of destroying Los Angeles. So we don't do that. But it was a proposal that we just do this and we'll never have large earthquakes again. Just triggering the large ones in those areas are kind of tough. So the last part of earthquakes is to look at this map and to talk about how, right, in these intro classes, a lot of times I say lie, we don't lie, we simplify things in these intro classes by saying earthquakes occur along fault boundaries. You know from our discussion of tectonics that we're looking at here, the conterminous United States, the North American plate, and we know that the plate touches the Pacific plate here, and then the little Juan de Fuca plate up in this top area. So based on that, based on talking about earthquakes happening at plate boundaries, we should not see a map that looks like this, right? Here is, we know that there are earthquakes mostly in the Big Island, right, because of this, this hot spot. And we've also discussed how the most seismically active part of the United States is actually the Aleutian Islands in Alaska. Lots and lots of earthquakes because that's, again, the Pacific plate and the North American plate are touching, sliding past each other. But this is a map from the USGS. You can look it up online. And you can see that there are areas, including our area, right? There are areas in the United States that have some increase in seismic risk. So the key here, the lowest hazard, where you wouldn't expect an earthquake, 0 to 2, is a white. And then as you go up to blue and then green, that's a mild to moderate seismic risk. You can see Boston, we're in this kind of moderate seismic risk zone. And then you get up to higher and higher yellow, orange, red, and fuchsia. You get to really kind of just expecting them to be there. So we will look briefly at the reasons why there are earthquakes in areas that, from a course point of view, we shouldn't be expecting them. Lower seismic risk. So on the one hand, right, it's not such a huge deal, right, because these are not areas where earthquakes are happening every day, but it's actually really bad. Some people think it's worse because people are not prepared. In Boston, we don't do earthquake drills in high school like they do in California. People don't know what to do. Also, the buildings are not properly constructed, especially older cities. Boston is going to have an earthquake, a big earthquake in the future, just a question of when. We've already established that there are earthquakes about every other day in Boston, so we may be in one right now. So this is really, really bad because Boston is built essentially of brick buildings. The newer buildings have to be earthquake-proof, but we don't have a lot of new buildings in this old city. So we'll look at these, again, briefly from a course point of view. Pacific Northwest, Puget Sound, there was an earthquake in 2001 that was magnitude 6.8. Nobody died, but there were 30 people that were caught in the Space Needle, stuck in the Space Needle, which probably was disconcerting, and there were about 400 people that were injured. This, again, is an earthquake that we geologists love because no one died, there wasn't a lot of damage, and we were able to trace the waves through the subsurface and find out a lot of information about the geology down in the subsurface. The reason that the Pacific Northwest has earthquakes and will have earthquakes, those who study earthquakes and will go on record as saying where they think the next big one will be, say that the Pacific Northwest, Washington and Oregon, are the places where the next big earthquake is going to happen. These transform boundaries like the San Andreas Fault sliding past each other, those are big earthquakes, but the really big ones happen at subduction zones. One plate, the Juan de Fuca plate, and diving down under the North American plate. And as you go deeper and deeper, that's more and more pressure. Remember we talked about confining pressure being a factor in how long rocks can bend. So when you go deep down in a subduction zone, the rocks are under more pressure and they're also a little warmer. They can build up a huge amount of energy, and then there's a tremendous release of energy. So big earthquakes, Washington, Oregon is the expected next huge earthquake in the United States because of this subduction zone. If you turn this sideways, right, the Juan de Fuca plate is diving down under the North American plate. A lot of what we'll look at in the mid part of the United States is based on pull-apart tectonics. The Basin and Range Province here, Arizona and New Mexico. In the 1950s, 1954, there were 3 earthquakes in this region, 6.6, 6.9, and 7.3. So this is, again, pull apart tectonics. What's going on is, and we'll look at this, we'll look at climate change as well. Here's the North American plate. The North American Orient, so you're looking at it like this. This is California, yeah. So the North American plate is moving towards the Pacific plate. This side, the California and down to Mexico side, is the active margin. So it is being actively moving. So there's a steep slope. There's not a big continental shelf, and it is the thing that's doing the moving, essentially. Where we are in Boston, we have an incredibly shallowly sloping coast. We have a big continental shelf. We're being passively pulled along by the active margin. So you have something called pull-apart tectonics. The plate is actually being tensely pulled, faster here, slower here. And so when you pull rocks like this, same thing with pushing them together or sliding things past each other, you can only build up so much tensional stress before one block of rock drops down relative to the other, and you end up with earthquakes. So this is continental rifting, the earth pulling apart. So basin and range province. Rocky Mountains are the same thing. I just put this in as a diagram. You don't have to worry about the time periods or anything of that nature. But again, this is pull apart tectonics. These are fault block mountains. What's happening is one side is moving faster than the other side. You're stretching out Earth, and one block of rock will drop down relative to another. And then you have weathering that's differential based on the height of the remaining structure. So pull apart tectonics of Rocky Mountains. We've already established that Hawaii is volcano related. So what's going on in Hawaii is and you saw this in the supervolcano film, right? So Yellowstone, same thing that's going on under Yellowstone that enabled them to make that computer model and predict what is beneath Yellowstone is, you can imagine here, magma's rising up from that hot spot, and the edge of the underground magma chambers cooling, sticking to the cool rock, and you have stick-slip behavior, so it's essentially sticking. These are not large earthquakes. You don't hear about people dying of massive earthquakes in Hawaii, but you can imagine that there are more earthquakes on the Big Island where you have that active hotspot, and fewer as you trail off towards the northwestern islands. This is an interesting area. The New Madrid earthquake was in the 1800s, 1811 to 1812. There are 1,874 earthquakes in this region, 2 over 7.5. They were felt over 1 million square miles. The church bells in Boston rang as a result of these earthquakes in this region. The Mississippi River temporarily reversed its flow. The reason why, again, this is sketchy and tough science, but the lithosphere is thin in this area. Some scientists feel that there was a divergent boundary starting to be created, right? So you're having a rift zone about 600 million years ago. Some scientists feel that this may have been an ancient hotspot, but something's going on beneath the lithosphere here that is causing a number of earthquakes right along essentially where the Mississippi River is. And this ancient rift zone they've termed the Real Foot Rift. And I'll show you a picture of the Real Foot Rift. These are sort of feathered arms of it. The recurrence interval is several hundreds of years. There was an earthquake in Charleston, South Carolina. It was a 7.3 in 1886, killed 60 people, and it was so strong it was felt in Cuba. So there are big earthquakes along this rift zone. And again, the recurrence interval is quite long, so people get lulled into a false sense of security if you have a recurrence interval of several hundreds of years. So that's roughly where the Real Foot Rift is. Us. We have earthquakes every other day. Puzzling. We have had big earthquakes, and I'll show you some of the big earthquakes that have happened. But there are really 5 theories on why we have earthquakes in New England. And the reality is 1 or 2 or maybe all of these in combination could be true. So 1, glacial rebound. Glacial rebound is a situation where during the last glacial maximum, New England was covered with about a mile thick of ice. You can imagine this is tremendous weight put on a huge region. this glaciation. So what happened was the crust, the lithosphere rather, was depressed. It was pushed down by the overlying weight of the ice. Now we're in an interglacial period. The ice melts back, and you've removed a weight, and so this pushing down, this depression, now can pop back up. So it's popping back up, rebounding. And it can just sort of slowly move, but every so often you get a break in the rock as a result of the crust being pushed, coming up to where it should be without that weight that was really kind of rapidly removed, speaking in geologic terms. Another idea is that perhaps there's an old Pluton, underground body of magma, that is or was there. There's some evidence of this if you look at anyone from Saratoga Springs, New York, from that area. Oh, okay. Yeah, oh, yeah, right. Awesome. Yeah. So there's bizarre water that has confounded. That's by training, I'm a groundwater geochemist, and it's the most amazing place to go ever. There's a vertical fault that goes right down into hell, not really, but straight down. And there's a signal of water that is bizarre. It's confounded people for a long, long time. There are all these springs there. There's 5 different water signatures. There's carbonated water, but it's cold. There's water that's so high in total dissolved solids that it's undrinkable. Some people think it has these magical, mystical qualities. But this is an area that shows that perhaps there is an old Pluton underground body of magma. The thermal pulse hasn't migrated up, but you're mixing the chemistry and the carbonates into the water, sulfates, all sort of volcano-related things. So it could be that there's an old Pluton there. Reactivation of a rift system, the feather arm of the Real Foot Rift coming up here and cracking, like the East African rift zone sort of curves around in Africa. So it may be that the United States, because of the Real Foot Rift, was or is, we don't know, pulling apart. And we will end up with 2 continents because there is a situation where tectonic convection cells are going like this under North America. You'll stretch North America thin about where the Mississippi River is, cut in 2. So feather arm of that comes up into New England. We also have, as a result of mountain building events, southwest, northeast regional compression. So we're squeezing from the southwest and northeast in this region. And so you're, instead of tensile, which is fracture zone movement, pulling apart, you're squeezing. And when you do that, you're pushing the rocks together. And again, you get a break. The last one is same thing, pull apart tectonics, right? We're being passively pulled along our coast as California is actively moving. And you have stretching thin, and there are fault blocks in our continental shelf. So that's cracking apart the rocks. So the reality is that, again, 1, 2, all of these could be the overriding mechanism. Could there be a big one? There are smaller ones, as you know, every other day. We count as a mild to moderate area of seismic activity. 1663 in Quebec, there was a 7.3. That was only 600 kilometers from Boston. 1940, Ossipee, New Hampshire, there was a 5.4. That was 176 kilometers from Boston. Remember 2001, maybe the Staten Island earthquake. It was only 2.6, but you could feel it. So there are earthquakes here. This is a picture of seismic events in this region. The one that we like to point out the most is the Cape Ann earthquakes, closest to Boston. Was in 1755, same year as the Lisbon tsunami, which we'll move to tsunami next. And certainly you don't have to read this all, but you can see this is a woodblock print showing in 1755 there was an earthquake, and it was so bad that there was a ship that was 300 kilometers to the east, and it was shook so badly that the people on the ship thought that the ship had run aground somewhere. The church steeples were toppled down, there was some fire, and so they thought it was about 6 to 6.5. So we will get one of these again. It's just a question of when. The last thing is, what should you do? And you can just read through this. There are all sorts of things that you can do. You have to worry about aftershocks, right? So